kick things off, we've got Elizabeth Yankovsky, who's currently working at Seaworthy, and she's going to tell us about mesoscale eddy vertical structure. So whenever you're ready.
Thank you very much. I'm really excited and grateful to be here to tell you about some of my work on mesoscale eddies. So today I'll be speaking about mesoscale eddies from both a modeling as well as a theoretical and observational perspective. This work has been done in collaboration with Scott Bachman, Jacob Steinberg, Schaefer Smith, and Laura Zanna. And for the most part, I worked on this work while I was a postdoc at New York University. And I should also mention that this work was part of a larger kind of NSF NOAA-funded project, which was the Ocean Eddy Energy Climate Process Team. And I'll speak a little bit more about that later in my talk. So to motivate what I'll be discussing, we all know that ocean turbulence has a lot of richness and variety across different scales that we encounter in our planet. So on the left-hand side of this slide, we see that we have planetary scale flows on the order of hundreds to thousands of kilometers, kind of shown in this model simulation up here. Just make sure this pointer is working. Yeah. And then on the right-hand side, we have non-rotational and three-dimensional isotropic turbulence, which we also see in the ocean. And so we kind of have this rich scale of kind of flows ranging from really large scales to really small scales. And my research primarily focuses kind of in the intermediate scales, so the mesoscale, which is tens to hundreds of kilometers, and then the submesoscales, which are on tens of meters to maybe 10 kilometers or so. And so this particular region is really interesting because it kind of marks the transition as well between the quasi-two-dimensional large-scale rotating flows and then the more three-dimensional type turbulence regimes. So in this talk, I'll be primarily focusing on mesoscale eddies, and I'll speak more about why they're so important and what the challenges are in understanding them. To give you an overview of where I'll go with this talk, I'm basically going to split it into two parts. The first part, I'll be speaking about mesoscale eddies in the context of climate modeling. So here I'll be describing why mesoscale eddies are very important in the broader climate system, as well as speaking about what happens when climate models do not fully resolve them, because it turns out that even state-of-the-art modern climate models do not fully capture eddy dynamics. And finally, I'll speak about my work in parameterizing eddies in climate models as well. In part two, I'll kind of move into a more theoretical aspect of this talk, and I'll discuss links between eddy horizontal and vertical structure from a geostrophic turbulence perspective. So a lot of work has been done on understanding some of the horizontal length scales governing eddy dynamics, but much less is known about their vertical structure. So I'll speak about kind of my work using both models and observations to gain insights into eddy vertical structure. Okay, so first I want to talk a little bit about the parameterization problem and why eddies are important here. So in general, when we speak about parameterizations, it's really in the context of modeling and the fact that we have finite computational resources. So here I'm showing a suite of 3 model resolutions. On the left-hand side is a 100-kilometer model. Sorry, that's the grid spacing. Let me just see why it's not playing. Yeah, and then the intermediate column is a 25-kilometer resolution model, and on the right is 10 kilometers. So you can see that as we increase the resolution, we resolve more richness in the flow turbulence. So we have more eddies at the higher resolutions, whereas in the 100-kilometer case, we're missing a lot of the important mixing and turbulent phenomena. And so the goal of a parameterization is if we have a coarse model that we can't necessarily afford to run at higher resolutions for long periods of time, how can we formulate a term prognostic equation or an embedded model that will allow us to kind of replicate some of the behavior of the higher resolution case while still maintaining computational kind of an expense. And so there's not necessarily a prognosed way on how to develop parameterizations, and can be quite challenging. And a lot of my work has been focusing on developing both mesoscale and submesoscale turbulence parameterizations. So I'll speak a little bit about what ocean eddies are, and then I'll kind of launch into discussing how I've approached parameterizing them. So from a very basic perspective, we can imagine eddies similar to a pendulum, where there is some sort of exchange between potential and kinetic energy. On the right, I have these very basic cartoons where I just have kind of a layered fluid. This top layer has hot and warm water side by side, This configuration, of course, is unstable. It has a great deal of potential energy in it. But if we allow this to evolve, what will happen is that there will be a slumping, and kind of the warm water mass will move under the hot water mass. And if we're on a large enough scale, this will become an eddy. So due to Earth's rotation. And so this process is kind of the baroclinic eddy process. And this is the main kind of dynamical phenomenon that I'll be focusing on when I speak about mesoscale ocean eddies. I should also mention that these are one of the major dynamical features that we see in the ocean, partially because we have such a large reservoir of potential energy that is set up through the differential heating and cooling of the ocean surface, and also through the winds. So the eddies are really important in the ocean for a variety of reasons. First, they comprise the bulk of the ocean's kinetic energy. I've seen kind of estimates like around 50 to 90%, depending on what you look at. They stir and mix oceanic tracers. They also set the stratification of the ocean, so this is very important for understanding layering. And as a result, they also have really fundamental impacts on the climate. So these include kind of carbon and heat uptake and sea level effects. And so on the bottom, I'm showing an image of these same three model resolutions that I showed earlier. So 100 kilometer, 25 kilometer, and 10 kilometer resolutions. And what's being plotted here is the globally averaged temperature drift as a function of depth on the y-axis and time on the x-axis at these three resolutions. And what you can see, particularly in the coarser resolutions, is that we have this bias of kind of warming in the intermediate layers and cooling near the surface, which is coming from the fact that eddies are not fully resolved in these simulations. We even see a little bit of that bias in the 10-kilometer case, although it's not as severe. And this is just a movie showing some of the surface chlorophyll from the GFDL ASM 2.6. And again, you'll observe that really this chlorophyll distribution is significantly modulated by the eddy signature. So it's really important, both from the standpoint of getting salinity, temperature, kind of the density structure of the flow to be correct, but also for understanding tracer transport problems, and as Mara talked about, some of the biogeochemical processes as well. So really kind of a fundamental problem is whether or not we can fully capture and or accurately parameterize eddies in our climate models. So to quantify this a little bit more, eddies in the ocean energy cycle. So here I'm showing a little movie of vorticity in the highest resolution case from the same suite of simulations that I showed earlier. You can see that there's kind of a lot of richness in the eddy field here. So what does this actually mean in the context of the overall energy cycle in the ocean? So as I mentioned, we have kind of large-scale forcing coming from buoyancy and from the winds that maintains the potential energy and kinetic energy reservoir of the ocean. These reservoirs can exchange energy with each other through the ocean circulation and through resolved mesoscale eddies. So mesoscale eddies, as I showed earlier, are extracting potential energy and converting it to kinetic energy. And so what happens if we do not resolve eddies? So in that case, this is the vorticity for the 100-kilometer resolution model. You can see that there's much less variability in the flow. And so we're missing a large component of this potential energy to kinetic energy exchange. And so the goal is to somehow parameterize this so that we can still obtain fidelity in our climate model solution. So there have been past approaches that have been quite successful, particularly for coarse models, such as this 100-kilometer case, in which we've attempted to parameterize the potential energy effects of eddies. So that's kind of illustrated in the cartoon on the bottom. This was kind of developed by Gent and McWilliams in the 90s, and this parameterization is known as the Gent-McWilliams parameterization. I'll refer to it as GM from now on. So you can see what this parameterization does is that it basically slumps these layers in a way that's consistent with eddy dynamics. So it's really correcting for the buoyancy structure by prescribing a diffusivity for these layers. So it can be thought of as a layer thickness diffusivity. And actually, this approach has worked very well for the past generation of climate models that were not eddy resolving at all. However, as we move into resolutions that now are starting to permit eddies, so kind of quarter degree or finer resolution climate models, it turns out that the momentum effects become increasingly important. So there's a new kind of approach to parameterizing eddies, which is known as backscatter, where we also attempt to represent the kinetic energy effects of eddies. So you may recall that I mentioned that eddies, the dynamical effect of them is to extract potential energy and convert it to kinetic energy. And so the backscatter approach attempts to mimic that process. Instead of only extracting the potential energy and assuming that it's dissipated, we are now extracting the potential energy and then artificially energizing the flow so that it has increased kinetic energy as well. However, the problem is that the physics of these backscatter schemes are still very poorly constrained. One big problem that I've been looking at is understanding the vertical structure of eddies so that we can perform the backscatter in a more physically informed way. Because we really need to know kind of where in the water column should we be injecting the kinetic energy in order to mimic the effects, or to mimic the quasi-geostrophic turbulence dynamics. So I've been working on this with this kind of climate process team that I mentioned earlier. So that's a picture of us. It's a multi-institution effort across a few different modeling centers, universities in the US. And in this effort, we developed an idealized modeling framework to really study eddy dynamics and to get a better understanding of what we're missing in the current parameterizations. So this idealized modeling framework, we called it Neverworld 2. There's another version of this, which is Neverworld 1 from some prior work. Basically, it comprises 4 resolutions. The coarsest one is 25 kilometers. So this is like an eddy permitting relatively coarse model. The highest resolution case is 3 kilometers. So I'll just show you a little bit of a video of that. This is the kinetic energy for those 4 resolutions. And really the goal of this model is to mimic some of the actual kind of properties that we see in the Atlantic basin. So there's like a channel in the bottom and enclosed basin in the northern hemisphere. And really to kind of isolate the effect of resolution and serve as a test bed for testing different existing eddy parameterizations and developing new ones. One of the interesting things about this resolution hierarchy is that it really allows you to see what happens as eddy resolution is decreased. So what I'm showing here is a few images showing to what extent we're resolving eddies in all of these resolutions. So the way that I define this is by taking the deformation scale, which is a dominant length scale for baroclinic instability, and dividing it by the grid spacing. So everything that's within this 2 isoline, I'm considering to be mostly eddy resolving. So you can see that as we move from this quarter degree case where we're mostly non-eddy resolving in the majority of the domain to the highest resolution case, which the horizontal grid spacing again is roughly 3 kilometers here, we're broadly resolving the deformation scale there. And so what happens as eddies are increasingly more resolved or not resolved? So as you may expect, the kinetic energy follows a pretty obvious trend. The lowest resolution model, which is the quarter degree case, has the lowest kinetic energy. And as we increase the resolution, the kinetic energy becomes higher. The potential energy also, you may remember, I mentioned that eddies extract potential energy. So as we resolve eddies increasingly better, so the pink line is the highest resolution, we have the lowest potential energy there, which again makes sense. However, as you may imagine, for the coarser resolutions, when the potential energy is overly high and the kinetic energy is overly low, we will be missing key processes that are going to modulate the tracer distribution, the stratification, and the energy pathways. The other interesting feature that I noticed in these coarser simulations is that the vertical structure of the flow starts to not be correct. So here I'm decomposing the flow into 2 components. This will become important later parts of my talk as well. So there's a barotropic component, which is the depth averaged component. And then there's a baroclinic component, which is the deviation from the depth average. And so here I'm showing kind of zonally averaged values for the barotropic and baroclinic components expressed as fractions of the total energy or the total flow. The yellow component is the baroclinic component, and the blue line is the barotropic component. You can see that at quarter degree, our flow is dominantly baroclinic, and when we move to the high resolution model, there's a great deal more energy in the barotropic part of the flow. And so we can get a little bit more insight into this by decomposing the flow into vertical modes. So these are the quasi-geostrophic flat bottom modes. So the 0th mode is the barotropic mode. Again, it's the mode that's uniform with depth. The blue one is the first baroclinic mode, and we can get progressively higher modes with more and more zero crossings. And so we can express these velocities as a sum of these modes, and then compute the energy in each of these modes. So that's shown here. So this is also a figure that Mario showed on Monday that kind of summarizes some of the energetics of the turbulent energy cascade. And I want to just spend a minute describing that. We can imagine that we have energizing of our flow that's happening in some of the baroclinic modes. And within the baroclinic modes, there is a forward cascade, meaning that energy is being moved to smaller scales. However, at the deformation scale, which is RD, we have kind of funneling of energy from the higher baroclinic modes and the greater baroclinic modes into the barotropic mode. So this is the mode that's uniform with depth. And so if it's uniform with depth, that means it's a two-dimensional flow, and it's going to exhibit the properties of two-dimensional turbulence, which is to cascade energy to larger scales. And so this process of the inverse cascade happens dominantly in the barotropic mode, and it's also known as barotropization, where we have kind of the flow becoming increasingly barotropic, and then the cascade of energy happens to larger scales there, where it is dissipated at the largest scales through bottom dissipation. So keeping this picture in mind, we can now look at this flow decomposition, where on the x-axis I have the mode number, so getting progressively into the higher baroclinic modes. Here I used a decomposition with 12 modes, which maybe is like a little bit overkill because most of the energy is in the lower modes. But nonetheless, you can see that there's a lot of energy here in the higher baroclinic modes at the lowest resolution. As we move into the higher resolutions, we see two things. One, there's more energy in the barotropic mode, which is the red bar, 0th mode. And two, there's just generally more energy to begin with. So this is really interesting because it's really giving us evidence that we're incompletely resolving the turbulent energy cascade when we fail to resolve the deformation scale, because we're missing this funneling of energy from the baroclinic modes into the barotropic mode. And so if we do not resolve the deformation scale, if we do not resolve eddies, this energetics is just not being captured. And so this was some motivation for me to start thinking about the backscatter approaches, where maybe we can energize, for example, the barotropic mode in a way that's consistent with the turbulence dynamics and get a much more accurate solution for our flow. And just to kind of emphasize that this indeed is a problem even in less idealized models than the one that I just showed, this is kind of looking at that CM2 model suite. So again, the same 3 resolutions that I showed earlier. And just taking a point off in the Argentine basin here and doing the same type of modal decomposition. And again, you see the same trend, where at the highest resolution we have quite a lot of energy, like more than 80% that's in the barotropic part of the flow. And then as we move into the lower resolutions, we see that the flow becomes increasingly more baroclinic as we fail to resolve the deformation scale, and also less energetic overall. So how can we parameterize some of these processes better? So going back to the energy cycle, this is a figure that I showed earlier. So we kind of spoke about how resolved mesoscale eddies are performing the potential energy to kinetic energy conversion. It turns out that you can formulate a parameterization by assuming this unresolved eddy kinetic energy reservoir. Here I'm denoting E as representing the subgrid eddy kinetic energy. And so the goal is to parameterize the interactions of this unresolved kinetic energy reservoir with both the resolved potential energy and kinetic energy reservoirs. As I mentioned earlier, the past parameterization approaches have really just kind of dealt with this Chapman-Williams component, where we parameterize the potential energy effects and then assume that all of that energy is dissipated. Here, we're kind of doing a different strategy, which is that we're also energizing the large-scale kinetic energy in a way that's consistent with these eddy dynamics. So in our budget for this, for the interactions of this unresolved kinetic energy reservoir with the resolved flow, we have these 5 terms. The first one is the potential energy extraction term, the GM term. Then we have a Smagorinsky viscosity, so this is just viscosity that's removing energy from the resolved flow, and it's acting as a source of energy for this unresolved kinetic energy reservoir. We also have this backscatter component, which is the component that's re-injecting energy into the flow, again to mimic eddy fluxes. And finally, we have the 2 terms at the end, which are dissipation and advection on the subgrid, and those are less important. And so if we look at the resolved momentum equation, this is a viscous term, so this is the Smagorinsky biharmonic viscosity, which is just removing momentum from the flow, removing energy from the flow. And this component is that backscatter component. So you can see that it's actually prescribed in a similar way as the dissipation, but it's acting as an anti-viscosity. So rather than removing energy, it's re-injecting energy. We have a Laplacian form to try to ensure that the energy is being re-injected at larger scales than it's being dissipated at. So here we have a higher order dissipation term and a lower order re-injection term. And so what I proposed is to prescribe nu2, which is the this anti-viscosity that's re-injecting energy, with an equivalent barotropic vertical structure. So previously, this was not done. There was no vertical structure. So whatever vertical structure the flow has, that's kind of what the backscatter was acting upon. And I proposed really solving for this more physical mode and applying the backscatter to that mode. And so to show you the results from that, here on the left is the truth case. So this is the high resolution 1/32 degree model. You can see that it's very richly eddying. There's a lot of interesting structure that you can observe there. On the right is the 50-kilometer grid. So this is actually a half-degree model. Everything else is analogous between the two. It's just the resolution is much lower. And on the right is the same 50-kilometer grid model, except it's using the existing kind of state-of-the-art scheme, which does not include vertical structure. So it's just like naively backscattering onto whatever vertical structure the flow already has. So when we really just backscatter onto the equivalent barotropic mode, not only are we able to energize the flow more, but you'll see that the character of the turbulence becomes much more realistic. So this is the parameterization that I've proposed with the vertical structure imposed on the backscatter. You can see that the energy magnitudes are multiple orders higher than these other simulations. And we really see a lot of similarity with the high resolution truth grid, even though our resolution is significantly poorer. And of course, this model is much less computationally expensive to run. If we look at what this does to our modal decomposition, on the left-hand side are the same 3 cases I just mentioned. So the unparameterized 50-kilometer resolution. This is just using the Jent-McWilliams component, so only parameterizing the buoyancy effects. And this was the prior approach where we have no vertical structure imposed on the backscatter fluxes. You can see in all of these cases, we have that problem of not enough barotropization. So our barotropic mode is consistently under-energized in these simulations. In my new parameterization, you see that, okay, maybe we're actually doing a little bit too much. We now have a lot of energy in the barotropic mode. So it's not perfect. This is also a point-wise measurement, so it's a little bit of a caveat. But overall, it's much more in line with the truth case, and we're definitely kind of succeeding in energizing this barotropic component of the flow. I should also say that one of the really cool aspects of this work is that if we energize the flow in a more physical way, so if we parameterize the momentum effects of the eddies better, it turns out that we actually correct the buoyancy structure as well. It's not perfect, but there are a lot of regions in the ocean where the buoyancy structure has been improved through imposing this backscatter with the vertical structure. So on the left, I'm showing the case with no parameterization. I'm just kind of looking at 3 different transects in different parts of that idealized model that I showed earlier. And I'm just showing the comparison between isopycnal positions between the case with no parameterization and the truth. So you can see particularly in the deeper parts in the ACC, we see outcropping of isopycnals in the wrong places. With our parameterization, that's significantly improved. And again, this is just stemming from the momentum parameterization. So it's really, momentum and buoyancy are very much related here. And here as well, we see that there's pretty significant improvement in the isopycnal structure. Of course, in the equatorial regions, it's not the case, but the eddy dynamics are less relevant there as well. Okay, so to wrap up this, this part of my talk, this component of the study offered two new insights. The first is that we can parameterize both the buoyancy and momentum effects that mesoscale eddies kind of create on the larger scale flow, just through a properly formulated kinetic energy backscatter. And the most important factor in having this backscatter behave physically is to have an accurate representation of the vertical structure of eddies there. And again, this is kind of a summary plot showing the kinetic energy and potential energy as a function of time for our parameterized case in blue and for an unparameterized case in red. The black lines are showing kind of the truth scenario. And you can see that we managed to get the kinetic energy of our half-degree model basically equal to that of the 1/32 degree model through this scheme. And at the same time, we managed to get the potential energy to match up almost perfectly, which I think was a really cool result. However, as I kind of showed in one of the figures earlier, it's not perfect. And if you think about the real ocean, there's obviously a lot of variability in the structure of eddies kind of in various parts of the ocean, and of course in their vertical structure as well. And so in the next part of my talk, I'm going to discuss a little bit more of what sets eddy vertical structure, and can we do better than just assuming this equivalent barotropic mode is the dominant mode of variability for eddies around the global ocean. So again, in this part of the talk, I'll be discussing some of the links that we can establish between looking at horizontal eddy structures and extending that to saying something about their vertical structure. So again, I'm showing this kind of diagram of the quasi-geostrophic energy cycle. And again, keep in mind that the inverse cascade in which the barotropization happens, it's really just in the barotropic mode dominantly. And we have the forward cascade in the baroclinic modes. So the goal here is to say, if we have some sort of surface measurements of eddies, like for example, we get the eddy scale, can we say something about what the barotropic to baroclinic partitioning of energy is going to look like for that eddy? And so in the 1990s, there were a couple papers by Larachev and Held that somewhat address this problem. They argue that the scale separation between the deformation scale and the eddy scale, or the energy containing scale, that governs how much barotropization we have. So the more space we have between the deformation scale where the eddies kind of start to grow and the final scale that they attain, which is RE, the bigger that ratio, the more barotropic energy we will have. And so they actually kind of formulated this linear relationship saying that RE over RD is equal to the barotropic to baroclinic partitioning. And so I decided to test that in this idealized model. So the way that I computed the energy containing scale is just by looking at the sea surface height deviations. You can also do this using spectral methods. But the result is shown in these two figures. So the ratio of the eddy scale to the deformation scale as a zonal average is shown in the red line here. And the barotropic to baroclinic eddy kinetic energy ratio to the 1/2 power is shown in the black line. And you can see that there is actually a remarkable agreement between those two. So again, this means that if we just look at the eddy scale and we know what the deformation scale is, we can say something about the vertical partitioning of energy. So how much energy is in the barotropic mode versus baroclinic mode, which is really powerful because as you can imagine, there's a lot of situations in which we just have kind of surface data. And this means that we can really infer the vertical structure of the flow just from surface observations. I will note that in the ACC, there's a little bit of a different dynamics. It's more complex there. Happy to talk about that separately. But in most of the domain, this works quite well. And again, this is like a very idealized prediction. It's for an F-plane in a QG idealized simulation. So it's really remarkable that it's working here. But can we continue to extend this to kind of more realistic settings? And so here I've been working with Jacob Steinberg, who is now at GFDL. And we wanted to test some of these ideas in observations. And so we considered 4 different mooring locations. So one of them is in the Argentine Basin over here, one of them is in the Southern Ocean, and then we have 2 in the north up here. And so what's being shown here are basically the total kinetic energy time series as a function of depth. So you can see that the time series for each of these locations look very different. In the Southern Ocean, so this location over here, we see that there's a lot of baroclinic structure. So near the surface, there's more kinetic energy, and the bottom of the ocean is relatively quiescent. Whereas if we look at, for example, the Argentine Basin or even the Erminger Sea, we see that the kinetic energy exhibits a lot more continuity from the surface to the bottom. So there's a lot more barotropic structure there. And so we wanted to test some of these ideas there as well. Can we predict what these eddy vertical structures should look like and what the partitioning between the barotropic and baroclinic components should be just through surface kind of scalings? And so we decided to kind of apply a high resolution model to get some more insight into this. So we used the same CM 2.6 tenth of a degree model. So that was that 10-kilometer model that I showed earlier, which is mostly eddy resolving throughout the entire ocean. And what we did was that we used this clustering tool. It's just like a k-means clustering that basically tries to identify similar velocity structures. So we took data points from the entire ocean and looked at the velocity, eddy velocity time series there, and then basically clustered them into these 5 different groups that are shown at the top. And what I'm plotting here is just the kind of standard deviation of the flow as a function of depth for each of those clusters. I should note that when we do this clustering, we lose all geographic information, so we just kind of concatenate all of these eddy velocity time series into one large matrix and then perform the clustering. So the fact that there's like some coherence in the geography of where these clusters are, that's purely a result of the clustering algorithm working. So you can see that, for example, cluster 1 tends to be a little bit more on the barotropic side. And we also see that in some of the higher latitudes, the Argentine Basin, as I mentioned earlier. And near the equator, we have a much more baroclinic type of flow. So this is cluster 4, for example. And so I wanted to look at each of these clusters and see if I could similarly come up with scaling relationships analogous to the one I showed earlier from Lerichev and Held that would explain the vertical partitioning of eddy energy in these different regimes. So this is kind of reminiscent of some of the talks that we've seen so far this week. So there are these 2 kind of ideas for different dynamical regimes. One of them is an F-plane regime, which again is kind of in line with the previous result that I showed from Lerichev and Held 1995, where at high latitudes we can kind of mostly assume that we're on an F-plane, and in that case, the scale separation between the eddy scale, LE, and the deformation scale, LD, governs how much barotropization we have and how much, what component of the kinetic energy is in the barotropic mode. For the beta plane case, so when beta is more significant, which happens at lower latitudes, in that case, it's the scale separation between the Rhines scale and the deformation scale, which is hypothesized by Held and Lerichev 1996 to govern that vertical partitioning. So rather than the arrest of the inverse cascade happening through bottom friction, here it happens through the formation of jets and through zoostrophy. Another paper, or a series of papers by Gaillet and Ferrari in 2020 and 2021 kind of revisited this problem. And they also, this is figure 1 from their paper, again reminiscent of some of what we've heard about this week, where they kind of look at Jupiter and identify the same sort of regimes. At the high latitudes or at the poles, we have this F-plane regime in which we have these individual vortices that are forming, and they call this the vortex gas regime. And of course, at lower latitudes, there are pretty striking jets that are being formed. So can we extend this to Earth? They argue that we potentially can come up with similar scaling relationships for the ocean, although of course it's not as clean as we see on Jupiter. But the idea is that at higher latitudes, again, we have F-plane dynamics, and at lower latitudes, it's more of a jet-driven dynamics. So in their paper, they define a parameter, which is the ratio of the Eddy scale to the Rhines scale. And they basically argue that when this parameter is greater than 1, we should be dominated by jet dynamics. So that means that the Eddy scale is actually feeling the Rhines scale because the eddies are larger than the Rhines scale. Whereas at kind of situations in which the Rhines scale is larger than the Eddy scale, that means the eddies aren't really being influenced by the Rhines scale. And so in that case, it's more of the vortex regime. And so they basically kind of define one as maybe a little bit of an arbitrary cutoff between these two regimes. But I actually computed that parameter for a subsection in the Pacific, kind of this box that I showed here. And it turns out that, yeah, around a little bit north and south of 20 degrees is where that transition happens. You can kind of see that actually just by looking at the vorticity, that we have a little bit more of a jet-driven type of dynamics at the equator. So then I had this hypothesis of what can we say about the vertical structure based on kind of the Rhines scale and some of these scaling arguments. So I created this chart to kind of summarize my thinking here. The first question is, are we near the equator? If we are near the equator, then we can assume that we're in the Geostrophic regime. So the arrest of the inverse turbulent cascade happens through the beta effect and through the formation of jets. In that case, the barotropic to baroclinic partitioning should be governed by the ratio of the Rhines scale to the deformation scale. So the bigger the scale separation between the deformation scale and the Rhines scale, the more barotropic energy we will have there. In this case, note that the bottom roughness is not important because the inverse cascade is arrested through zonostrophy, not through bottom friction. If we are not near the equator, then I'm saying we're in the vortex regime and the arrest of the inverse cascade happens through bottom drag. So in that case, the character of the bottom becomes very important. If the bottom is smooth, in that case, we can assume that the barotropic to baroclinic partitioning should be governed by that F-plane relationship that I showed earlier, where the Eddy scale divided by the deformation scale is what governs how much barotropization we have. And if the bottom is not smooth, then I'm hypothesizing that it's the topographic Rhines scale, which is kind of an analog of the traditional Rhines scale, but taking into account topographic gradients, which also affect the PV of the flow, to the deformation scale. So there are these kind of three regimes, and I was hoping to test out looking at the barotropic to baroclinic partitioning in all of these clusters and try to argue as to whether or not we can say something about the vertical structure of the flow just by looking at these horizontal length scales. Okay, and so I just want to spend 2 slides on the bottom roughness because it turns out that that's very important, especially for the regime where we're not near the equator and the bottom is not smooth. So this is showing the slope of the bottom, so the slope magnitude over the global ocean. This is a figure by Jacob Steinberg. And the way that this is computed is just by taking like a one degree box and computing a plane to best fit that box. So you can see that there's quite a lot of regions in the ocean where the slopes are relatively significant, where the flat bottom mode approximation does not work. We can also look at the roughness, which is just the deviation from that slope that we compute. And so that kind of a high roughness just means that there's a lot of topography fluctuations. And so we can actually bin the roughness distribution in this histogram. And one thing that Jake and I did was that we took the smoothest topography class and we kind of tried to map that onto the barotropic to baroclinic kinetic energy ratio. So I think this plot is super cool because here we can see that this is just showing the barotropic to baroclinic partitioning of the kinetic energy. And you can see that there's a lot of variability over the ocean, but we tend to see more barotropization in the higher latitudes. And the really cool part about this is that if we look at the smoothest topography class that I showed in the previous histogram, we can overlay this on top of the barotropic to baroclinic ratio, and we actually see that where the topography is the smoothest, that's where we have the highest barotropization. So you can kind of think of that as the situation in which the inverse turbulent cascade is the least inhibited. There's no topographic beta effect or almost nothing. And also the planetary beta is quite weak at these high latitudes. And so I think that's a really cool result, just kind of seeing that the smoothest topography at the high latitudes really aligns with the strongest barotropic flows. But looking more broadly, so going back to those clusters that I showed earlier, I subdivided them into two cases. So the top series of plots shows each cluster that is basically in the latitudinal regions within the equator, so minus 20 to 20 degrees. And so that is kind of using the scaling relationship that I mentioned for the equatorial region, which is that the barotropic to baroclinic kinetic energy ratio is given by the scale separation between the Rhine scale and the deformation scale. So here I'm plotting that ratio of Rhine scale to deformation scale, and on the y-axis is the barotropic to baroclinic ratio. And again, you can see that this is aligning remarkably well. I mean, this is like a very idealized theory, and we're looking at a kind of realistic model results here. But nonetheless, like the one-to-one line is shown in black, and we see pretty good alignment between these two parameters. So again, this means that if we just have a measure of the Rhine scale and the deformation scale, we can predict roughly what the barotropic to baroclinic partitioning of energy should look like. So now we can look at the higher latitude regions. So this is outside of the equator. And here I'm arguing that for the majority of the ocean where the bottom is not smooth, it's really the topographic Rhine scale that is arresting the inverse cascade, and that's going to govern kind of how much barotropization we see. So here, again, plotting the same thing, barotropic to baroclinic EKE ratio, and then that Rhine scale divided by the deformation scale. And again, we see really, I think, interesting matchup between these two parameters. And particularly in cluster 1, which is that more barotropic cluster that we see at the higher latitudes. I didn't show it in this figure, but if you also filter out kind of the smooth versus rough topography, we really see excellent matchup between the vertical structure of the energy and that kind of scaling relationship. Okay, so I'll wrap this up here. So basically, to summarize what I've talked about, we began by talking about Eddy vertical structure in the context of climate modeling and in the context of parameterization development. So I showed you this development of backscatter parameterization that takes into account Eddy vertical structure when we parameterize the kinetic energy fluxes that eddies are initiating, but we're not actually resolving in the model. And again, we saw that if we take into account the vertical structure, we are able to energize the flow much more similarly to our truth scenario, and at the same time also improve the buoyancy structure of the flow. And then we talked about kind of the scaling relationships to explain regimes in Eddy vertical structure using both observations and high resolution model data. So again, just to summarize, I kind of looked at these 3 different regimes, one of which is the Geostrophic regime near the equator, where our barotropic to baroclinic energy partitioning can be approximated by the scale separation between deformation scale and Rhine scale. And again, the argument there is just how much of a spectral space do we have for the inverse cascade to happen. And then the vortex regime, in which case we have 2 scenarios, one where the bottom is smooth, and we observe that Held-Larachev scaling where the scale separation between the deformation scale and the Eddy scale sets the barotropization, and the rough bottom case where topography is acting to inhibit the cascade. And I'm happy to take questions. Thank you for listening.
Very interesting talk. I wanted to know in your model resolutions where you're changing the resolution, did you keep the bottom drag constant, or did that vary with resolution?
The model drag was kept constant, yeah.
Okay. Well, do you think that's justifiable? Do we know that the bottom drag should be constant as we go to infinite resolution? I mean, ultimately it's molecular viscosity and turbulence we have going on over topography, and do we really know what the bottom?
Yeah, I think that's a valid question. We had a lot of discussions in how to formulate the dissipation closures in this model, where we varied the resolution. Our final kind of idea was that we wanted to keep as many of the model assumptions constant as possible, because otherwise it would be hard to attribute what if we changed, the viscosity parameterization as well as the bottom drag, what's coming from that change versus the Eddy resolution. So we kept
the reason I say that is I'm concerned that the barotropization that you're seeing could be because your bottom drag is way too high at high resolution. That's all. So I wonder if you should check whether that goes away a bit as you reduce the bottom drag.
Yeah, that's definitely a valid point. I did show the comparison with the other model, the CM2 suite, which kind of had a similar trend, but I agree, it's not as, the barotropization, like the component of the kinetic energy that's in the barotropic mode isn't as different between those resolutions. And I do agree that in general, in that idealized model, we were seeing flows that were maybe too barotropic, kind of in a global sense. But it is an idealized model, and it's hard to get all aspects of it correct. So it's a good point, though. Thank you.
Yeah, could you go back to where you showed the Smagoritsky model,
Yeah.
please?
This equation? Or...
Yeah. Okay, that looks like a Smagoritsky model if you were doing DDT of del squared U. You see what I mean?
Yeah, so this is actually, I should note that I wrote it in this form for simplicity. The more correct way to write that term is using a strain rate tensor. So instead of del squared U, it should be del strain rate tensor.
Okay.
Because then you can account for the fact that the viscosity varies in space and time. I just thought this would be easier.
All right, thanks.
Bruce?
I'm trying to understand how, the physics that underlies barotropization. So if I have near the surface some slumping of isopycnals, how does that, from the point of view of kinetic energy, create an acceleration in the abyss? If that's the right way of thinking about it.
Yeah, I think you can think about it in terms of Eddy. So let me go back to. So this this kind of picture of decomposing the flow into vertical modes. Of course, like the first baroclinic mode is exactly what you're saying, which is kind of intensified near the surface and decreasing to kind of something very small near the bottom. But in reality, there are higher modes as well that have more complex vertical structures, and these modes interact with each other. And through their interactions, they move energy into graver modes. And eventually, they move energy into the barotropic mode as well. I guess it's a little bit of like a theoretical construct in some ways.
Is there, you focused on eddies, I mean, is there perhaps an internal wave component where the internal waves are interacting to create this barotropization?
I think that could be a factor as well. Here I'm focusing primarily on like eddy interactions and maybe like triad interactions.
Yeah, that's buried inside of that term, backscatter term even.
Yeah, I think it kind of depends on the resolution of your model, whether it's able to capture some of the internal wave dynamics. But it could. I mean, I think if you do have internal waves and they're being dissipated by the viscosity in the model, that will serve as an energy source that will potentially drive barotropization. Yes. Thank you.
Mary Louise?
Yeah, thanks, Elizabeth. So in our observations, as you know, when an eddy sort of grazes a mooring, especially when they're higher modes, baroclinic mode eddies, it's really difficult to tell their vertical and horizontal length scales. And so you can do it by satellite if it's a barotropic mode, or and so we rely on the deformation radius to a certain extent to say something reasonable about their scales.
Yeah.
So can you now use this to help us a bit better interpret if we have reasonable measurements of EKE, say?
So EKE from like a vertical profile, for
Yeah.
example. I think that can definitely be used. I was kind of viewing it from the starting point of we have surface data, now what can we say about the interior? But I think the same applies backwards. So if you have a good measure of the barotropic to baroclinic partitioning in the vertical, then I think by also knowing the stratification and maybe the deformation scale, you can say something about the Eddy scale from that using the same relationship. Yeah, thank you.
Peter?
I was wondering what the potential vorticity structure of the eddies looks like when you go to differing resolution, right? I mean, have you looked at that at all?
The
I
potential.
mean, you described sort of the baroclinic becoming more barotropic as you go to high resolution. I was wondering how that was kind of manifested in potential
Potential vorticity. I haven't looked at the potential vorticity very much. I just kind of looked at the surface distributions of it, but I imagine that it would follow a similar structure as the energy. But yeah, I can definitely take a look at that a bit more.
Yes, I've got a question for you. So you've got these three regimes with this kind of different partitioning. And your first part of the talk, you're talking about, barotropization and how you're inputting this. Is there a way now, moving forward, where you can take your different regimes and incorporate that in your parametrization, or are you sort of talking about different?
Yeah, I think that's a great question. So the parametrization, as I formulated it, it takes like a pretty basic, just the equivalent barotropic mode, which has kind of a large amplitude near the surface and decays to near zero near the bottom, and basically applies that everywhere. And yeah, as you said, there's actually a great deal of variability in the vertical structure, and that particular mode is not necessarily appropriate everywhere in the ocean. So we started to implement this in a global climate model, and in fact, there are regions where it's a little bit problematic, particularly around the Southern Ocean. And I think that could be a really interesting next direction of this work, is to try to incorporate more information into the actual vertical mode that we're using. One interesting result that another scientist in the climate process team is working on now is testing out the surface quasi-geostrophic mode as an alternative vertical structure for the backscatter. And it turns out that at higher resolutions, that actually works a little bit better than this equivalent barotropic mode, because you're capturing more of the barotropization, I think. But I think that's a great future area to look at, is how do we maybe have a map of modes, or how do we just inform the vertical structure better as a function of the location? Yeah.
Yeah, Matt.
Can you go to the slide with your momentum equation?
Mm-hmm. Yeah. This one?
Yeah. So which of those is putting kinetic energy in?
It's this one, so the backscatter component. It's prescribed as basically in the same way that you would prescribe a Laplacian viscosity that would dissipate energy, but in this case, the sign of the viscosity coefficient is opposite.
U2 is negative.
Mm-hmm. Yeah, and so it's just injecting energy back in. Yeah.
Chris?
I quickly just ask about this kind of the energy budget here as well,
Yeah,
and what the difference between the Smagorinsky and the dissipation in this the div T is, because like I'm used to thinking of Smagorinsky as sort of a subgrid version of doing sort of dissipation. So what is the EDIS?
So yeah, the EDIS is just a bottom drag. You mean this term, right? Yeah, so we still have Smagorinsky viscosity operating on the momentum equation of the resolved flow, so we're still removing energy through the Smagorinsky scheme. But then we also have this subgrid dissipation term, which it's just assuming kind of that energy is dissipated through barotropization. And that term actually, I can show you another plot that shows the magnitude of all of those terms. So this is just like the actual value of E as a domain average, or like as a 500-day average over the entire domain. And then basically that E dot nu2 is the energy source, the energy backscatter component, and E dot nu4 is that Smagorinsky component. So yeah, it's kind of, those two terms are really the dominant terms, and then the friction and advection components are pretty small. So here I wrote EDIS as E fric, but it's the same thing. It's relatively negligible over the domain.
Okay, so it's like small scope dissipation and large scope dissipation.
Yeah, exactly.
Any last questions for our speaker? Okay, well, let's thank Elizabeth again.